Hello everyone, this is Annal Mercy, Assistant Professor, Department of Mathematics, Fatima College, Madurai. I am going to explain the ratio test and which comes under the topic series of real numbers. So in this video, you learn about what is ratio test and how it applies to check whether a series converges or diverges. To check the nature of the series, we are going to use the ratio test, right? So the statement of the ratio test is given. So whenever you take a series of real numbers, so you take the limit supremum of this ratio to be capital A, and small a is the infimum of the uh, ratio an plus 1 by an. So according to the values of a, we can conclude about the series nature, right? So we are going to learn about this through this theorem. So this is otherwise called D'Alembert's ratio test. The theorem statement that sigma an be a series of non-zero real numbers. Let a equal to limit n tends to infinity infimum of modulus of an plus 1 by an, and capital A is the limit supremum of modulus of n plus 1 by an, with a condition that small a is less than or equal to capital A. It is clearly the case the infimum is always less than the supremum, right? So therefore small a is less than or equal to capital A. Then if capital A less than 1, then the series summation modulus of an is less than infinity, which means this series, that is summation modulus of an less than infinity, means we say that the series summation an is absolutely convergent, right? So this is the first case, absolutely convergent. And in the second condition, if small a is greater than 1, then we say that summation n is equal to 1 tends to infinity, an diverges. And the third condition is, so what about the other cases? For a greater than or equal to 1, and for the other case a less than or small a less than or equal to 1. In that cases, we cannot apply the ratio test. That means this test cannot be applied to check the convergence or divergence, right? So this is the theorem statement. So by finding the ratios, we are going to calculate. By finding the ratios, we are going to calculate the series nature, right? So that's why this is called the ratio test. So let us see the proof of this theorem. So let me use the conditions. So it is given that, so just you are taking a series of real numbers. Your series is summation an, right? So for this an, we are calculating small a, which is given as limit n tends to infinity infimum of modulus of an plus 1 by an, right? And another one is capital A equal to limit n tends to infinity supremum of modulus of an plus 1 by an, right? So this is what the capital value of a, right? So we are going to prove the first condition. So let us prove the first result, right? So the first result is given as if a less than 1, we are going to prove that if small capital A less than 1, then the series is absolutely convergent, right? So this is the first condition we are going to prove. So that look at here. So I am going to consider, I am just assuming that capital A is less than 1, right? So what is capital A? A capital A is limit supremum of the series modulus of an plus 1 by an. So this is what given here, right? So by using this, we are going to prove this theorem, right? So for this, I am going to use this theorem, which we have already studied in the previous sequence unit. So let Sn be a bounded sequence of real numbers. You consider a bounded sequence, and if limit supremum, so you are finding the limit supremum of the sequence, then for any epsilon greater than 0, Sn is less than m plus epsilon for all but a finite values of n, and Sn is greater than m minus epsilon for infinitely many values of n, right? So I am going to apply this theorem statement. So I am going to apply this and I am going to prove this, right? Because we are given the limit supremum, right? So limit n tends to infinity supremum of modulus of an plus 1 by an is given. As I told you, I am going to use this theorem, right? So I am going to use this theorem. So what is this theorem says? This theorem says that limit n tends to infinity supremum of supremum of Sn is m, right? So this is what they have given. So when supremum is given, you can write this Sn is less than that supremum plus epsilon, and also this is true for all but a finite values of n, which means that Sn is, I can write, அவங்க கொடுத்துருக்குது அந்த சீக்வன்ஸுக்கு, so the sequence is modulus of an plus 1 by an, right? So this is your sequence, so I can write, so modulus of an plus 1 by an is less than, okay, less than, I can write a plus epsilon for all but the finite values of n, right? Or for all but the finite values of n, finite values of n, which means that I can say that this condition an plus 1 by an is less than a plus epsilon, and this is true for all n greater than or equal to capital N. So this is true for, this result is true after the values which are greater than capital N, right? So this is what I am taking. So இந்த மாதிரி தான் எடுத்துட்டு I am going to, so actually this is already, this is true, right? So how we are going to prove it, right? So how we are going to prove the proof of it, right? So listen here. So now what I am going to do is, since they have given capital A is less than 1, I am going to choose B, choose a value of B such that this B is lying between A and 1, right? So which means, shall I say that then I can say that then there exists some epsilon such that B equal to A plus epsilon. Shall I write like this? So which means I can say that ஒரு எப்சிலான் ஒரு வேல்யூ வந்து, அதாவது ஏ கூட ஒரு சின்ன வேல்யூவை ஆட் பண்ணோன்னா அந்த வேல்யூ, அதாவது ஏக்கும் ஒன்றுக்கும் இடையில என்னால் ஒரு பியை என்னால் கேல்குலேட் பண்ணிக்க முடியும். அதை தான் நான் என்னென்னு எடுத்துக்கிறேன், கேபிட்டல் பின்னு நான் கேல்குலேட் பண்ணிக்கிறேன். அப்போ இதை நான் என்னென்னு எடுத்துக்கலாம், இதை கேபிட்டல் பின்னு எடுத்துக்கலாம். ஸோ இதை வச்சு ப்ரொசீட் பண்ணுறேன். therefore I will get an plus 1 by an is less than b for all n greater than or equal to capital N, because I have taken b to be a plus epsilon, right? So since this b equal to a plus epsilon, I can write an plus 1 by an is less than b. So this is less than b for every n greater than or equal to capital N, right? So by applying this, what shall we get? So I can write, so now you choose your n to be, so since this is true for every n greater than or equal to capital N, now you choose n equal to capital N. So what will you get? an plus 1 by an is less than or equal to b, and this is true for, so I can take this. So I have chosen your n is equal to capital N. So similarly, I am going to consider now n to be n plus 2. So what? N, take your n as n plus 1, because this is true for every n greater than or equal to capital N. When you choose your n to be n plus 1, so you can write n plus 2 divided by a n plus 1 less than or equal to capital B, right? So now what I am going to consider is a n plus 2 by a n. So from in this, so I am going to write this to be as a n plus 2 by a n plus 1 into an plus 1 by an. I can just multiply and divide by a value, right? Since mod a into mod a b is equal to mod a into mod b, I can write an plus 2 by an plus 1 into an plus 1 by an, right? So already we know that from the previous result, what we know, an plus 1 by an is less than or equal to b, and an plus 2 by an is less than or equal to b, right? So I can write, so this is less than or equal to b, and this is less than or equal to b. So what can I write? So I can write, so this is equal to an plus 2 divided by an. So this is less than or equal to b square, right? So next I can write, so for any, so similarly I can continue the results, right? So what can I write? an plus 3 by an. In the same way, I can write this by an plus 3 by an plus 2 into an plus 2 by an plus 1 and I can write an plus 1 by an I can write. So which means, so all these values are so I can split the modulus an plus 3 by an plus 2 into modulus of an plus 2 by an plus 1 into modulus of an plus 1 by an. I can write like this. Already what we know, so these values are less than or equal to. So this is less than or equal to b, and this is less than or equal to b, and this is less than or equal to b, which means I can write an plus 3 by an. This is less than or equal to some b cube, I can write, right? In the same way, if you take any k greater than or equal to 1, I can write an plus k by an. So this is less than or equal to b power k. So I can write like this. So now what I am going to do is I am going to split the modulus. So I can write modulus of an plus k by modulus of an. This is less than or equal to b power k, and for k greater than or equal to capital N. So from this I can write an plus k by an plus k modulus of an plus k alone I am going to take, right? So I can write this to be modulus of an plus k less than or equal to mod an into b power k I can take, right? So I can take this to be modulus of an into b power k, and also I can say k is greater than or equal to capital N, right? So which means what will you get? So actually I am getting this result. Now what I am going to do is I am going to apply another theorem, right? So I am going to apply geometric series theorem. So we know that since the value of b, we know the value of b, right? So we know that b is greater than 0 and less than 1. So I'm going to apply a theorem, geometric series theorem. The theorem says that if 0 less than x less than 1, then I can say that the series summation n is equal to 0 to infinity x power n converges to 1, converges. Okay, so it converges to some value, but I want only the convergence. So similarly I can apply, since the value of b is lying between 0 and 1, I can say that summation, okay, so I can say that summation k equal to 0 to infinity b power k converges. B power k converges. Again, modulus an is a constant, which means I can apply summation k equal to 0 to infinity modulus of an into bk is also converges, right? So this is converges. So now already what is the result we have? So this is the result we have, right? So what it says, modulus of an plus k less than or equal to modulus of an into b power k, it says, right? So actually this is true for, so this is the result we have. This is true for every k greater than or equal to capital N. So actually I can say that the first series is, if you consider this to be a series, the first series is dominated by the second series, right? So I know the nature of the right sign series. So it is converges, right? So it converges. So I can apply the comparison test, right? So by comparison test, we know the comparison test, right? So when the first series is dominated by the second series and the second series is converges, means I can say that the left side series is also converges. So I'm applying that by comparison test. I can say that summation k equal to 0 to infinity an plus k, modulus of an plus k converges, I can say. So I can say that modulus of an plus k converges, right? So which means what? So I can say that modulus, so this is modulus. So I can say that modulus of a1 an plus modulus of an plus 2 n plus 1 plus modulus of an plus 2 plus etc. So this is a convergent series, right? So this is converges. So which means I can say that the series summation n equal to 1 tends to infinity modulus of an converges, right? So this is, so converges, right? So which means I can say that summation n is equal to 1 tends to infinity modulus of an is less than infinity, right? So we have proved the first result, right? So now we are supposed to prove the second result, right? What is the second result says? We have to prove that if small a value is greater than 1, then we have to show that summation n is equal to 1 tends to infinity, an diverges. An diverges, right? So how shall we prove this? So for this, what I'm going to do is I'm going to apply again the same theorem, right? I'm going to apply the same theorem. So I'm going to apply the same theorem. So for that, I'm going to consider, since a is greater than 1, since a is greater than 1, I'm going to choose, right? So I'm going to choose a value epsilon greater than 0 such that I'm going to choose a value epsilon greater than 0 such that a minus epsilon equal to 1. Since it's a value greater than 1, definitely you subtract something from a, you will get the value equal to 1. So let the value be epsilon, right? So choose such epsilon, right? So now what I'm going to do is I'm going to apply this theorem, right? So I'm going to apply this theorem. What is this theorem says? And also we know about small a, right? Your small a is nothing but, it is given that it is nothing but the limit infimum of the series modulus of an plus 1 by an, right? So this is the limit infimum of the series, right? So this is the limit infimum of the series. So what can I do? So I'm going to apply this theorem here. I'm going to apply the second result of the theorem. It talks about the infimum, right? So infimum, right? So let us take this condition, right? So what is given? If the infimum of the sequence equal to some m, then Sn is greater than m minus epsilon for all but a finite number of the values of n. So I'm going to apply this result. So you apply this result for this sequence, right? So when I apply this result for this sequence, what will I get? So by the theorem, I can say that modulus of an plus 1 by an is greater than a minus epsilon, and this is true for all but the finite values of n, right? So this is true for all but the finite values of n. So what shall I write? So I can write an plus 1 by an is greater than a minus epsilon, and this is true for every n greater than or equal to capital N. So what I get? So I can write here modulus of an plus 1 by an is greater than 1, and this is true for every n greater than or equal to capital N, right? So here you choose. So again, when you choose n equal to capital N, so you will get modulus of an plus 1 by an is greater than 1. So which means you can write modulus of an plus, you can split the modulus and you can write, so this is greater than modulus of an, right? Similarly, when you substitute n equal to capital N plus 1, you will get modulus of an plus 2 by an plus 1 is greater than 1. With this implies modulus of an plus 2 greater than modulus of an plus 1, right? So when you proceed like this and you take, when you take n to be n plus k, so what will you get? A n plus k divided by a n plus k minus 1, this is greater than 1. This implies modulus of a n plus k, this is greater than modulus of a n plus k minus 1, right? And so on. So it will be going on, right? So now I'm going to compare all these and I'm going to write as a result. So what we have, modulus of an is less than. So when you compare and write, you will get modulus of an is less than modulus of an plus 1. This is less than modulus of an plus 2. This is less than, and so on. This is less than modulus of an plus k minus 1. Less than modulus of an plus k, less than, and so on. So it will be going like this, right? So which means you are getting, the terms are getting greater, right? So when it is getting greater, definitely I can say that the terms, the sequence terms are getting larger and larger, which means I can say that the sequence an does not converges to 0. I can say that this sequence an does not converges to 0, right? Which means that I can say that the limit of the sequence an is not equal to 0, right? So there is a theorem which says that, we have studied a theorem The theorem says that if the series summation n is equal to 1 tends to infinity, an is convergent. The theorem says if an is convergent, then limit n tends to infinity, an equal to 0. We can write the same theorem as if limit n tends to infinity, an is not equal to 0 means I can say that the series summation an is not convergent. So the same concept I'm going to apply here. So what is this result says? This result says if sigma an limit n tends to infinity, an is not equal to 0, then the series need not be convergent. So here also we are getting the limit of the sequence. So since the limit of the sequence is not equal to 0, I can write the series summation n is equal to 1 tends to infinity, an is not convergent, right? So not convergent mean I can conclude that the series summation n is equal to 1 tends to infinity, an diverges, right? So this is the second part. So we are going to prove the third case. That is when small a less than or equal to 1 and less than or equal to capital A, we are going to prove that the test fails. So for this, I am going to consider two sequences, namely summation 1 by n and another series is summation 1 by n square. Let us check the nature of both the series and we can conclude this result, right? So let me find out the limit of the sequence. So we have to calculate it. So before that, let me write what is an in the given sequence, right? So let me calculate what is an in the given sequence. So I am writing an to be 1 by n, right? So I can write an plus 1 also. So an plus 1 is nothing but 1 by n plus 1. Now let us write what is an plus 1 by an. So an plus 1 by an is 1 by n plus 1 divided by n 1 by n, which is equal to n by n plus 1. So let us calculate the limit of the sequence. So the limit of the sequence an plus 1 by an is nothing but limit n tends to infinity n by n plus 1. So we can write this to be limit n tends to infinity. You can, when you apply the limit, you can take n outside. So what will you get? 1 plus, take n from the denominator, right? So when you take n outside, 1 plus 1 by n we get. So this is nothing but, so what you are getting? So you are getting this is equal to limit n tends to infinity 1 by 1 plus 1 by n, right? When n tends to infinity, this term will get 0, right? So 1 by 1, so the limit value equal to 1. When limit of the sequence exists, since limit n tends to infinity, an plus 1 by an equal to 1, limit exists means the limit supremum as well as limit infimum are same, right? Limit supremum of an is again 1, that is capital A equal to 1, and also you can say that limit n tends to infinity, infimum of an plus 1 by an is also equal to 1, right? Which means, look at here, so we are getting both the values are equal, and we are and also already we know the nature of the series. The series is a divergent series, right? So already we proved that the series is a divergent series. So look at here, so we are getting from a small a as well as capital A value to be 1, value is 1, but in this case we are getting the nature of the sequences, so divergent sequence. Look at this sequence. Actually this is a harmonic series. So the harmonic series, there is a result, the harmonics, about the harmonic series, summation n equal to 1 tends to infinity, n 1 by n power p is convergent if p greater than 1, right? So p greater than 1, since the value of p is 2 here, so it is a convergent series. So now let us check the limit supremum and the limit infimum, right? So you can consider an is nothing but 1 by n square. Similarly, we can calculate what is an plus 1. So an plus 1 is 1 by n plus 1 the whole square. You can write this to be n square plus 2n plus 1, right? So now let us calculate the ratio. So which is an plus 1 by an. So this is equal to 1 by n square plus 2n plus 1 divided by 1 by n plus 1 the whole square. Which means I can write an plus 1 by an equal to n plus 1 the whole square divided by n square plus 2n plus 1 I can write. So now let us calculate the limit. So limit n tends to infinity an plus 1 by, okay, so actually what is an? Sorry, your an is nothing but 1 by n square, right? So here also you'll be getting that is equal to 1 by n square, right? So here it is 1 by n square, so it is n square divided by this term. So what is limit n tends to infinity an plus 1 by an? Limit, so again I am writing this in the next line, limit n tends to infinity, okay, n square divided by n square plus 2n plus 1, right? To simplify, let us take n square out from the denominator, right? So when you take n square out, n square into 1 plus 2 by n plus 1 by n square, right? So that's all. This n square get cancelled when you apply the limit. So what will you get? Limit n tends to, substitute limit n tends to infinity. When n tends to infinity, this value equal to 0, this value equal to 0. So and the denominator value will be equal to 1, right? So here the limit of the sequence an plus 1 by an equal to 1, which means again, since the limit is equal to 1, limit supremum, that is small a equal to 1 as well as capital A also equal to 1. So look at here, we are having two different cases, right? So we have actually considered the series summation 1 by n, which is divergent in nature, whereas the another series summation 1 by n square, which is convergent in its nature. But look at here, in this convergent, so here also in the both the cases we are having the limit supremum and the limit infimum values are equal to 1, right? In both the cases we are having limit infimum as well as limit supremum values are equal to 1, right? Limit supremum values are equal to 1, but we are having two different cases. That's why we are saying that we cannot conclude under the case when a less than or equal to small a uh, less than or equal to 1 as well as capital A greater than or equal to 1, right? So under this case, the results are unpredictable. That is, the nature is, it is, we cannot conclude that the series is convergent or divergent because there exist, when this case occurs, there exist series which have a nature as diverges as well as converges, right? So therefore under this case the test fails. Okay, so that's all. Thank you.